Well, as you can already tell, those slopes of the tangent lines must be slightly important. So, for that reason, the slopes of tangent lines are given a special name, and their name is, by the way, derivatives. And if we're talking about function f, for function f with a little mark up, superscript, I guess you call it, line like this, that for function f is said to be the derivative of the function. And it should be noted, f with a little mark, which, by the way, we read that f prime sometimes, but it does mean the derivative. F prime, f derivative of f. We'll call it different things at different times, but f prime for short is, and f prime is the slope of the tangent line at each particular value. Okay, so if I have f of x, then y equals some, well, we'll talk about that. All right, so on the handout there, for this particular section anyway, what I've got there is I've got three graphs. Let's focus in on graph Roman numeral 1, which looks a lot like this. Give a little draw here. See, that's -1, then it goes 1, 4. Looks vaguely like it, doesn't it? Okay. This crosses here at 2, -2, I'm sorry. It's -1, this is 4. Yeah, that low point's more over here. Okay. I think that's pretty good rendition. We'll go with it. All right, so that's, we're calling that y equals f of x. We'll get to those others here in just a second. So what, first of all, just getting used to the notation and what it means. First of all, what I want to do is estimate f prime of 3. What do you think that means? F prime of 3 is, by definition here, or what we're calling it, this is telling us to take the derivative at 3, come up with the derivative at 3, right? F prime is the derivative. However, on graphs, we have to interpret what the derivative is. Now, what is the derivative? The derivative is the slope of the tangent line at 3. So in this case, at 3. So this is what I want to do. I want to estimate the slope of the tangent. So it's the derivative at 3, but the derivative is, let's do it this way. So I want the derivative at 3, but the derivative at 3 means the slope of the tangent at 3. Well, we've done this previously, right? We just had a little different context, but now we're calling it the derivative. So, yeah, so I just come here at 3. Now I'm not really liking my drawing, but okay. But on your paper there, yeah, so like we did way back when, I'm just going to come here at 3. There's my point, the function value. That's the point there. And drawing a tangent line. Not my best one ever, but okay. Draw your tangent line there. Matter of fact, I think I will do it on the paper here. And see what slope you come up with. It looks like it's a positive slope, definitely a positive slope. And doing my rise to run thing, I'm looking here, here's what I'm seeing. This point here at 2 is about, it's about negative 3.5. Should have been, but yeah, it's about negative 3.5, supposed to be. Anyway, so it's negative 3.5 there, and then I've got another point here at, it's a little off there at 4, but yeah, this this one, it's about negative 0.5. So I'm rising from negative 3.5 to, so that's about a rise of negative, 3, and then a run of 2. So I'm saying 3 halves. 1.5. Yours may be slightly different, but that's what I came up with. Is that close to what you got? Okay. So we're just doing a rise to run thing because that's, by definition, really what the derivative is equal to on the graph. It's the slope of the tangent line. All right, what do you got at for estimate? You do this one. Estimate f prime of negative 1. F prime of negative 1. See what you get there. Anybody got it? What'd you get? Don't want to say. Okay. Somebody jump out there. Tori, what'd you get? Positive or negative? I'll go with that first. It's definitely a negative. Yeah. All right. So I'm going here. So I'm going down. There's my point. So I'm going a tangent line there. Okay. And what I saw was mine hit pretty well. It was just above, here's 2, and this was just above that. And then I went down and over 1. So it was about 2.1, a fall of negative 2.1, and then a run of 1. That's what I got. Yours may be slightly different. It's fine. It's just an estimate anyway. I got about negative 2.1. So negative 2, negative 3, negative 1.5-ish. Okay. Anything in that range, somewhere negative 1, negative 2, something like that. Is that what you got? Even close? What you got, Nick? You got negative 2.5? Okay. So yeah, that'll vary a little bit for some of these, but you get the idea. You're just doing the rise to run thing and see what you get. Okay. All right, now here's one we need to get right on the dot though. What is the derivative at 1.5? And again, these are the x values. I don't know if I actually said that, but right, these are the x values. So I'm looking at the derivative at the x value of 1.5. Well, isn't 1.5 the point right here at the bottom, so to speak? Okay, so the tangent line would be horizontal. Is that what you get? And what about horizontal lines or horizontal tangent lines? What's the slope there? Well, you don't rise any, you run whatever, 0 over whatever, 0 over 1, 0 over 2, is 0, isn't it? Yeah, when you get those horizontal tangent lines, remember the slope is 0. And so 1.5 is where we have that horizontal tangent line. So the slope there is 0. So the derivative is said to be 0. So really, all we're doing right now is we're going back to what we were talking about, the slope of the tangent lines, but now we're calling it the derivative. The derivative is the slope of the tangent line. We've done all this before. We're just doing it now in the context of derivatives. Okay? All right, so let's see. I got a second one on the handout there. So let's go to graph number 2 for just a second, just to make a point here. You know, that we had a nice curve there, but on number 2, what kind of graph do we have there? It's just a straight line, right? I called it g of x. So there's just kind of a special, let's see, 1.5, so negative 1.5, positive 1.5 are my intercepts there. So anyway, here's what I wanted to mention on that. You know, slopes of the tangent lines for those curves, we understand that, but what about the derivatives here? G prime of 2. Well, the thing's a line itself, and so drawing its tangent line is a little bit tricky, isn't it? The thing is already a line. So this is talking about the slope. Just think of it as the slope. We'll get to at some point where we'll say the derivative is the slope of the curve. What's this? This is really wanting a slope, right? And lines, well, they have slope, so that's really what it's about here. You're not really going to draw a tangent line in because it's already a line. You're just going to come up with the slope of this line. What is the slope at 2 here? Well, it looks like the function value is about 1/2, isn't it? That's 1. Yeah, so all I have to do is really the rise to run, go rise over run from one point to another point there. So on the thing I'm seeing rise, well, if I rise 1 and then I run 1, rise 1, run 1, it looks like a slope of 1. That's what I get, okay? Close. If you get close to that, that's pretty good. But here's the thing. What is g prime of, what about at negative 1? Well, again, that's the slope at negative 1. Since I've got a line, I'm just thinking slope. So here's, yeah, it looks like the point's down here at about negative 2.5, but again, if I rise 1 and then run 1, that looks like what it would be. Yeah. This line has the same slope here as it does here as it does here. So whatever derivative you want, it's the same thing. For a line, we say, so g prime of 3 would be 1. They're all the same. The derivative of each x value for a line, it's going to be the same thing, whatever your slope is. It's constant. The derivative is going to be constant for a line. You know, for a nice little parabola there, well, it was negative, 1 was positive, we had 0. So, you know, if you have a curve, the derivative is going to change because your slope changes. Slope's not going to change for a line, so the derivative is going to stay constant. Whatever it is here, it'll be the same here, whatever. Okay? With me on that? Sound okay? All right. So I've got a third one on there. Let's see. Here's a third type of question number 3. We've got an h of x. it's looking somewhat like this. -1, -2, +1, +2. Intercept there, 1, 2 there. High point about there. Point there, there. Okay. Just kind of getting it close to what you got there on the paper. All right. Sort of what it looks like. Here's what I want to do. List these in increasing order. H prime -1, H prime +1, H prime 2, H prime 5, and H -3. That last one is not a prime, it's just a H. We'll take a moment there, see what you get. Put those in increasing order. So smallest first. Start with the smallest. Increasing order. So smallest one first, next to smallest, third smallest. See what you get. All right. Maybe you got them, maybe you don't, but what'd you get? Well, here's what I sort of came up with. First of all, the one I'm seeing here, well, let's just kind of, here's what I got. H prime at -1, I came up with to be about 1. H prime at -1, so we're talking right about here. So I was seeing it, yeah, if you rise 1, you run 1, you got it. Okay, so +1. H prime of 1, the derivative, the slope of the tangent at 1, well, there, if you draw the tangent line in, draw the tangent line in there, you definitely get a negative. I kind of went here, over 1, and then down. It's about, I got it about a -1.5. Get close to that, something close to that. H prime at 2, well, that one was easy because that's right here. You got a horizontal line, so that's slope 0. At 5, well, the 2 on the end, probably the interesting ones there. H prime at 5, that's kind of way off the chart, isn't it? But what would you say as far as its slope goes? Very large? Medium? Well, if you think about it, this thing is slanted pretty good right here. So if I go on up, yeah, if I go on up out there, I'm talking pretty steep tangent line, steep tangent line, so it has a large slope, a large positive number. Let's just say it that way, okay? So that one's one you really can't get maybe a number on, but I guess you could if you had more paper, but it is going to be a large positive. And then the last one. The last one is not a derivative, please note. Once again, that's just a function value. H of negative 3, I'm just talking about the function value at negative 3. That has nothing to do with the slope, it's just the function value. Well, and once again, I'm off the chart a little bit, but I estimated if I went on down, it's going to be, that point is going to be somewhere around negative 10 or so. And since I'm not talking the slope, is it a positive value or negative value here? It's a negative value. It's negative 10. The slope's positive, but that's not what that's asking for, you see. To be the slope, it has to have that derivative. So that's kind of the point here. This is just talking about the function value at negative 3, which I see is about negative 10. It could be more, it could be less, I guess. But so all told, which one's the smallest? That h of negative 3 is the smallest. Then I'd have h, what would be next? H prime 1. Then I have h prime 2. Then I'd have h prime negative 1. And then h prime of 5. Is that what y'all got? Smallest to the largest. Okay? All right. So anyway, knowing that connection there, that's important. That the derivative is the slope of the tangent line. So if it asks for the derivative off of a graph, we're just doing the slope of the tangent line. Okay? All right. We'll come back to graphs probably more next time, but for now, that's what I wanted to get on the graph part of it. However, you know, back when we were going through it, you know, we started estimating. You know, we drew our graphs. Then we went to tables, right? We did a table of values. We got some secant lines going. But ultimately, we wound up finding slopes of the tangent lines. Well, we either use definition 1 or equation 2. I said we'd probably focus more on equation 2. So remind me what that. Yeah, we wound up saying, well, the slope of the tangent was equal to the limit as h approaches 0 of f of a plus h minus f of a over h. That was equation 2. Equation 1 was, was f of x minus f of a over x minus a. So one of those two we used ultimately to start coming up with the slope of tangent lines. Well, now that we know derivative is the slope of the tangent line, guess what this also represents? It's a derivative. The slope of the tangent is that, and the slope of the tangent we know is the derivative, so this, the way I've got it, would be the derivative at a. Yep. That equation 2 comes right in handy with doing derivatives. Turns out the derivative at a, we don't have to estimate it because if we've got the function, we can find it exactly by doing this limit thing. Now remember what it was. This, well, that kind of describes the secant line, right? The difference of the y's over difference of the x's. You know, the a plus h minus a would be the. But this is those secant lines. This is what we had. Say we're coming in here at a here. Well, if we take a secant line out here, we go out h, a plus h, a little bit there. Then we get this other point, come up to the point there. Okay, so we've got this secant line. That's a comma f of a. That one's a plus h comma f of a plus h. And so if we do our MPQ thing, we've got f of a plus h minus f of a over a plus h minus a. The a's cancel, so we wind up with that. So why do we do that? Well, we want h, this distance h, going to 0, don't we? The closer and closer we get to a, letting h go to 0, we get the slope of the tangent line. Well, the slope of the tangent line just happens to be called, now we call it the derivative. It's all the same. We've done all this. We're just now calling it derivative. Okay? All right. And so, that is what we're going to do here a couple of times anyway. All right, so let's find f prime of a for f of x equal x squared minus 5x plus 4 Well, you know, the derivative does equal the slope of the tangent. However, by our definition of derivative now, we know that it's the limit as h approaches 0, f of a plus h minus f of a over h. What do I do with that? Well, very same thing we were doing not too long ago. What does this mean to do? Well, it means plug in. I don't have necessarily a value to plug in, so I'm just going to do f of a plus h. What is f of a plus h? Well, that means input a plus h, in for x, so it would be a plus h squared minus 5 times a plus h plus 4. Then I have minus f of a. Well, f of a is going to be x, plug in the a, okay, be a squared minus 5a plus 4. All that divided by h. What do we do with that? Do all the math, all the algebra there, all the good stuff. Square that square that a plus h out, a plus h, right? What do you get? You get a squared, ah plus ah, that's 2 ah's, and h squared. Distribute the minus 5, so it'll be minus 5a minus 5h plus 4. And then over here it is minus all this, so that'll be a minus a squared plus 5a minus 4, wouldn't it? So the top becomes that. Is that okay? Look all right? All that over h. With me so far? Nice things happen, right? A squareds cancel. I got a minus 5a, I got a plus 5a, I got a plus 4, I got a minus 4. What's left? Well, I got 2ah and h squared, and then I got a minus 5h. Looks like an h can come out of those, doesn't it? Pull an h out of that, so it'll be 2a. H out of that will be plus h. H out of that will be minus 5. H's cancel. Now I can do my limit, can't I? The problem was I couldn't go to 0 because that was h on the bottom. Now the h on the bottom's gone. What's the limit? 2a. H is going to 0. Minus 5. It's called the derivative of a. Derivative at a. Okay.